Hello everyone, my name is Balaji Selvakumar and I'll be presenting our work on deep point cloud building envelope segmentation or deep cubes using deep learning. This research was conducted at Oak Ridge National Laboratory, supported by the DOE Office of Energy Efficiency and Renewable Energy. Our project focuses on creating digital twins of older energy inefficient buildings that lack building information models. These digital twins are essential for accurately capturing the current state of these buildings, and thereby they can help in designing and fabricating prefabricated panels used in retrofitting. By using point cloud scans, we aim to create accurate BIM models which facilitate the efficient retrofitting of these structures. Retrofitting can greatly improve their energy efficiency and help reduce costs. DeepCubes aims to achieve high accuracy, save time, and reduce human error. Let's start with the problem we are trying to address. Many of these older buildings lack detailed BIMs, making retrofitting a challenging task. Traditional methods for BIM modeling and digital twin generation involve visual inspection and manual measurements, which are often time consuming and prone to errors. These measurements are then manually used to create the wireframe model. Our goal is to automate this process by collecting LiDAR point cloud scans of these buildings and using deep learning segmentation methods to automatically segment and create accurate building wireframe models. This automation not only reduces human error but also saves significant time, enabling more efficient retrofitting of older buildings to improve their energy performance. In this slide, we compare the different methods for building segmentation. Manual segmentation requires high human effort and is not scalable. Photogrammetry and sensor fusion methods need label data and they have to be retrained for different architectures, and the resolution is not high and is more error prone because most of the work is done in 2D and not in 3D, thereby losing the depth information. Our approach, Deep Cubes, aims to combine the advantages of LiDAR with supervised learning, offering higher accuracy and scalability with less human intervention. This is crucial for retrofitting older buildings efficiently. Our scan to BIM digital twin generation workflow involves several steps. The first step is to scan the buildings using a LiDAR scanner and collect point cloud data. This point cloud data is later processed and segmented using our AutoCube software into different types such as windows, doors, roofs, and facades or wall points. AutoCubes uses unsupervised learning to precisely segment the facade. These label data are stored as a part of our ordinable library. All the label data in our ordinable library is validated with manual measurements collected using our total station. From the validated data, we train multiple deep learning models to perform semantic segmentation, and the output of these segmented facades are used to create the digital twin with as-built dimension. As a part of our Oak Ridge National Laboratory Building Envelope Library or ORNABLE, we have scanned and labeled over 25 building point clouds, thereby creating a diverse dataset for training and testing the models. The diversity of the dataset ensures that our models can handle various building architectural types and conditions, which is an essential part for retrofitting older buildings. These are some of the images of various types of facades that we have scanned across our campuses. We are actively collecting more building scans and they are labeled and validated with the ground truth data. This makes sure that the model will be able to learn and segment a wide variety of facades once trained with enough data. We validated the AutoCube segmented data with manual multi-point measurement across the windows. We collected multiple points across the perimeter of the windows, since measuring corners introduces human errors. From the collected points, we did PCA and fed a bounding box, and that gives us the dimension of the windows, and these are considered as the ground truth data. Um, our dataset currently includes over 223 million labeled and validated points with features like XYZ coordinates, RGB values, intensity, and labels. We are also evaluating additional radiometry features like planarity and curvature for helping the model learn the features better. This image is like a sample of the from the label data, and red color represents the openings or windows, and blue represents the wall points, and green represents the other classes which currently has extrusions of the building. Uh, this is the cluster distribution. As you can see from the picture and the data, the point cloud is heavily imbalanced because of the inherent nature of the number of wall points in the scan. So, so for our model selection, we went with PointNet++ and SuperPoint Transformer, both of different architectures. PointNet++ uses MLP-based architecture, whereas SuperPoint uses transformer-based architecture, which has seen a fundamental breakthrough in language and vision domain in recent times. It can also be trained on additional pre-computed geometric features such as curvature, linearity, planarity, etc. While training PointNet++, the model failed to converge, so we had to artificially balance the data by removing 80% of the wall points to make the model learn the features, whereas SuperPoint Transformers was able to learn really well on the class imbalance data. The way SuperPoint Transformer works is that it tries to partition the point cloud into semantically homogeneous superpoints, which are based on the features that I mentioned before. Then the model learns to classify these superpoints. That way, the model is like really efficient in terms of compute, and it tries to learn the features, semantic features, really well. So here are some of the preliminary test results from both PointNet++ and SuperPoint Transformer. The image on the left is the PointNet predictions from PointNet++, which was tested on artificially balanced data. So, and these are the raw predictions from SuperPoint Transformer, which is much better as it works on the point cloud as it is. And these are the error metrics from the SPT compared with the ground truth. Our median is pretty close to the target 3 millimeter that we are trying to achieve, and we are actively training with new improved features. So, in conclusion, our approach automates folding envelope segmentation, reducing human error and saving time. We have created a well-labeled dataset with diverse facade label scans, and we have also explored some data augmentation methods for balancing the data. These are some of the results. This is the result as produced in the paper, and these are the results that we have experimented after publishing the paper with additional features such as curvature and point normals. This way the model is able to segment much better. So our feature work involves creating newer subclasses and establishing a level of detail in the digital twin generalization, and also exploring post-processing segmentation pipelines. Thanks for providing me the opportunity. Let me know if you guys have any questions.